Okay, in this next section, we're going to take a look at how to analyze acids and bases using a technique called titration, and then we'll jump into some math problems using titration calculations. But let's first discuss what titration is. Titration is a really common technique that's used in analytical chemistry. So it's a procedure where one solution, and I'm just going to abbreviate solution here as SOLN, and usually it's a base, is added to a second solution. But the base we have usually has a known concentration, first of all. So that base, like I said, is added to a second solution of unknown concentration. Sorry for all the abbreviations. I know this is a lot of writing though. But that second solution is usually an acid, at least in this portion of the textbook. All right. So like I said, we're going to add our base into our acid. We know the concentration of our base. We don't know the concentration of our acid. However, the volume of base can give us a lot of clues. So the volume of the solution added can be measured. And it can be used to determine the concentration of the second solution. All right, so I know this is a really long definition, but let's see what this looks like in practice, because it makes a lot more sense when you actually see it performed. So here's an image from the textbook describing what normally occurs during a titration. So over here, we've got step one, right? So step one is to basically use a calibrated pipette that's really accurate and add a known volume of your acid, right? So at this point over here, you have a volume is known, but concentration is unknown. All right. And then what we can do is we can then take this solution down here and we can put it on basically a lab stand like this, or a ring stand. And this thing above it is called a burette. It's basically a big upside down graduated cylinder that can dispense liquid out of it. And so we can use all of these graduated markings, like right here, here, and here, to measure the volume at the beginning and then the volume at the end of our titration. And then what we can do is we can say, well, if it moved, let's say, this much, we know how much volume was dispensed into our unknown acid. And because we know the concentration of this, so we can measure the volume. That way it's known. And then second, it has a known concentration. We can do some math to basically back calculate out the amount of moles in this unknown acid, or the concentration of it, since we know the volume as well. All right, so I know it's a little bit weird to think about, but it's commonly done, and there's a few more terms that we need to describe. The first is called the equivalence point. And this is what we're often looking for in a titration. The equivalence point is the point where the unknown solution has completely reacted So if that unknown solution was an acid, it means we add enough base to completely neutralize the acid. So that's the point where the solution has completely reacted and there is no excess acid or base. Let me just put no excess solution from either source, because sometimes you do this without an acid or a base. All right, so that's the equivalence point we're often looking for. Oftentimes you'll hear the term endpoint too. All right, and these are closely related. So oftentimes the trouble with an equivalence point is when you neutralize an acid and a base, it's colorless, right? So what an endpoint is it's the point where we stop the titration due to some sort of indicator that we've added. It's basically our stop sign for us to know when to end. So this is the point at which the titration is stopped on the basis of an indicator. All right, and these indicators vary a little bit. It's usually either a pH probe, meaning we can just see the readout of the pH of the solution, or commonly we use these color indicators, in which case there's a noticeable color change of the solution underneath the burette telling us you need to stop right now and measure the volume dispensed. All right, so let's take a look at some of these color indicators, because not all of them are the same. And this is a image from the textbook, but on top right here we've got methyl red. It's a common color indicator, and as you can see, there's kind of a color change in between this range, right? So it looks to me like this color change happens between 4 and 6 as a pH, maybe 5. So methyl red would be a good indicator if you're looking for an equivalence point that you know will be within that range. All right, underneath it, this is called bromothiol blue. And this one is a little bit different. Here you can see the equivalence point is right around pH of 7. So if you're doing a strong acid, strong base titration, where that equivalence point is just creating salt and water, this might be a really good indicator, because it'll tell you if you've added too much base, for example. It would switch to blue really quickly and you'd say, ah, I'm done. I've reached that equivalence point. And then in the last one here, we've got phenolphthalein. And again, you can tell this one's a little bit different. It's got a color change, again, kind of between, I don't know, it's kind of near pH 8, I think. So depending on the pH of the equivalence point, we might select a different indicator so that we can detect when the endpoint is reached for that given titration. All right, so like I said, usually when you're doing these titrations, you do it with an acid and a base. So let's go through a few sample calculations. So I'll just say example 1. Okay, and in example 1, we're going to do a strong acid, strong base titration. So I've got my acid, it's HNO3, and I'm going to react this with my strong base, sodium hydroxide. And because it's a strong acid, strong base titration, we're going to always get out water, and we're going to get out our salt, which in this case is going to be our leftover cation, sodium, and our anion, nitrate, and this will be aqueous. So let's make a few notes here. We've got our acid, we've got our base, we've got water, and we've got salt. The only time we get CO2 is if we're dealing with carbonates or bicarbonates, but we don't have that here, so we're not going to worry about CO2 as a byproduct. All right, so in this sample question from the book, it says, okay, our acid, we measured out with our pipette into a beaker, and we've measured it really well at 25 milliliters. However, we don't know the concentration, right? So this is unknown. That's what we're trying to solve in this titration. And we had to add in the sodium hydroxide dropwise until our indicator changes color. And we were able to tell that we added in 16.3 milliliters were added before we got the color change on our indicator. We also know that the solution was 0.200 molar because we made that solution. It was a known quantity. So the goal is to use math to find this unknown concentration. Okay, so let's do this first. So first, let's find the moles of the unknown acid. Okay, so let's go ahead and do the math for this. And this just basically becomes a big stoichiometry unit conversion problem. Okay, so we know that we had to add in the 16.3 milliliters. So that's where I would start. That was our known direct value. So I'd say 16.3 milliliters of NaOH were needed, right? But here's the tricky thing. If you remember, molarity is always moles per liter, not moles per milliliter. So what I would want to do next is I would say, let's get this to liters, so then we can use our molarity unit. So I'd cancel out milliliters by putting that on bottom. And I know that 1 milliliter is equal to 10 to the negative third liters. And the reason I know that is this prefix milli is the same thing as 10 to the negative 3. So I'll go ahead and put 10 to the negative 3 on top, but now we've canceled out our milliliters and milliliters down here, right? So we're good to go there, and this was our unit conversion we used in that step. But we can't do a liter to mole conversion without using our molarity unit. So that's when our molarity is going to come in. So if you remember, up here, we said it's 0.200 moles per liter. Okay? So we could basically plug this in and we could say 0.200 moles of NaOH per 1 liter of NaOH, right? So this is our molarity being used as a conversion factor right now. Okay, and this is great because now we can cancel out liters, and now we have moles of NaOH. Moles are the universal currency for stoichiometry, so that's always my initial step, is find your way to moles. Okay, now that we're there, we can look at our reaction, right? And our reaction is already balanced, meaning I didn't need to add any coefficients here. We've got the correct number of atoms on each side. So what that means is we have 1 mole of NaOH for every 1 mole of nitric acid. So we can use this to cancel it out, right? So I'd cancel out moles of NaOH down here. And we know we get 1 mole of HNO3. So like I said, these are the reaction coefficients from the balanced reaction. So now we can go ahead and cancel out moles of NaOH, and we're left with moles of nitric acid, right? So not too bad. We can go ahead and type this into our calculator, and I'm getting 0.00326 moles of HNO3, our nitric acid. Okay, so let's make a note here. So there must be this many moles in our 25.0 milliliter sample. All right, so we figured out the moles of our unknown acid. Okay, let's do part 2. Part 2 would be find the molarity of our unknown acid. All right, molarity and moles aren't the same, right? So if you remember, molarity has the symbol M, and it's equal to moles over liter, right? Well, we already figured this part out right here, so I could go ahead and plug that in. So let's go ahead and do that. So I would say that there's 0.00326 moles of HNO3. And I know the volume that we had was 25 milliliters, not liters, right? So I'd do the same thing I did before. I'd say, well, if we have milliliters, we need to convert it to liters. So I'd say, well, we essentially need to do the same sort of conversion that we did up here, right? So cancel out milliliters, get to liters. So 1 milliliter is equal to 10 to the negative 3 liters. I normally put this all in parentheses to prevent calculator errors. Parentheses are my best friend whenever I do stoichiometry. It avoids any mistakes in the calculator. So now we can go ahead and calculate this. We should have 3 sig figs that come out. So I'm getting 0.130 molar HNO3. So we were able to use stoichiometry and titration to find the concentration of this unknown acid. All right, let's do one more problem for those of you that want to stick around. We'll do example 2, because I know sometimes it's a little tricky to see these. Okay, example 2 will be another strong acid, strong base titration, but this time we're going to use H2SO4. This is our acid, and I'm going to react it with NaOH, and this is going to be our base. We know that we're going to get water out, right? But now let's try to figure out what our salt would be. And I'll give you a hint, right? If we go over here, we would say, well, this is going to break apart into 2 protons, right? Because it's got 2 of those right there. Whoops. So that should be 2H plus. And we'd be left with SO4, and it must be 2 minus, right? To counteract the 2 protons that were lost. Okay, let's do the same thing over here. If this splits apart, we'd be left with the sodium cation plus the hydroxide anion. So we know that these 2 pieces are going to combine to form our water, right? Which leaves us with this and this left over. However, the sodium only has a +1 charge, where the SO4 is 2 minus. So that tells me that I need to have 2 sodiums for every 1 SO4 unit, right? In order for those charges to cancel. All right, so if it helps, break them into their parts. This acid over here, sulfuric acid, is unique. It's one of those diprotic acids, which means it gives up 2 protons. All right, so we're not done yet. I'm going to erase this just to keep things organized. But what I'm seeing here is an unbalanced reaction, right? In particular, I've got 2 sodiums here, and I've got 1 here, right? So let's fix that. Let's put a 2 in right there, and now we've got 2 sodiums on both sides. All right, but we're not quite done yet either. If I look at my oxygens over on the right-hand side, I've got 1 plus 4. I've got 5 oxygens. Where over here, now I've got 4, 5, 6. I've got 6 oxygens. All right, so what I would do is I would put a 2 in front of this, and now if I double check everything, it looks like everything is balanced. All right, so before we do much else, I always recommend balancing an equation. It's essential for stoichiometry. So we're taking this acid, we're reacting it with this base, we're getting 2 equivalents of water, and we're getting our salt over here. Okay, so same setup as before. I'm going to measure out exactly 25 milliliters of my unknown acid. So this has an unknown concentration. This is what we're going to find. Okay, and in the titration, I had to measure out 32.6 milliliters of sodium hydroxide before I reached the end point of the titration. And maybe there was a color change that let me know that I reached my equivalency point. All right, and we know the solution was 0.200 molar. All right, so same idea. We'll break this into 2 parts, kind of like we did before. First part is let's find the concentration, moles of H2SO4. All right, and like before, I start out with the volume of my base. So I'd say, well, we use 32.6 milliliters of sodium hydroxide. Just like before, I don't want to work in milliliters, I want to work in liters. So I'd say 1 milliliter is equal to 10 to the negative 3 liters. That way I can cancel out milliliters and get to liters. And then next, we need to get to moles, but this time, just like before, we need to use molarity. So it's set up almost identical so far to the problem above. So 0.200 moles of NaOH per 1 liter. So now we've canceled out liters here. Okay, but we need to now convert from moles of sodium hydroxide to moles of sulfuric acid. So I'm going to put moles of NaOH down here. And I'm going to put moles of H2SO4 up here. Well, if we go and we look at our balanced equation, it looks like we've got 1 mole of sodium hydroxide to 2 moles of sodium hydroxide, right? So down here, I would want to put a 2 with the sodium hydroxide and then the 1 with the sulfuric acid. So it looks really similar, but if you don't balance the equation, you forget this step and your answer is all wrong. So you do need to go through and do the stoichiometry. Okay, so I went ahead and checked this on my calculator, and I'm getting 0.00326 moles of H2SO4. All right, now 2 would be find the molarity of H2SO4 for this unknown acid solution, right? Okay. Well, we know molarity is going to be equal to moles per liter, and we just said that the sample has 0.00326 moles of H2SO4. And we know from the question description that we measured out exactly 25 milliliters of it to use with our titration. So I'd say, well, 25.0 milliliters, not liters, which means we need to convert it to liters. And I'd say, well, let's go ahead and do the conversion like we did before. Cancel out milliliters, and now we're left with moles over liters. Okay, and now that we're done, we can go ahead and do the math, and this is 0.130 molar. Oops, and this is H2SO4. And for those of you playing along at home, you might notice that the molarity is the exact same as the prior problem, right? So I just said that this was 0.130 molar, and up here that was 0.130 molar. But let's go back and double check all the stuff. So you see how in example 1, we added 16.3 milliliters of sodium hydroxide, where in example 2, we had to add 32.6. Well, this all of a sudden makes sense, right? Because we had to add twice as much because sulfuric acid is a diprotic acid. Means we need twice as much base to soak up twice as much protons, right? All right, there's a lot of good practice problems in the book, but this is really excellent stoichiometry review. It's a good way to check not only your understanding of this chapter, but to review stoichiometry problems from previous chapters. So I would really recommend trying to work through some of these at home and then check your work using some of the answers in the back of the book. All right, I hope that helps, but let me know if you have any questions.